So good day everyone. In this video, we are going to discuss the proof by contraposition. But before that, let us quickly discuss what a direct proof is. So a direct proof leads from the hypothesis or premise of a theorem to the conclusion. So if we want to prove this conditional P implies Q, we start with the assumption that P is true. And with that, using that assumption, we prove that Q is also true. So there are some theorems or proof of theorems that do not begin with the hypothesis or the premise and end with a conclusion. So those are called as indirect proof. So proof by contraposition, which comes from the word contrapositive, is an example of a indirect proof. So first, we assume that not Q and show that not P is true also. So if we give a direct proof of the contrapositive not Q implies not P, then we have a proof for the original na implication P implies Q. So not Q implies not P is an indirect proof of P implies Q. Okay, so why does this work? The implication P implies Q is already proven to be logically equivalent with its contrapositive, not Q implies not P. So how can we prove P implies Q from its contrapositive, not Q implies not P? So we first assume not Q is true, and so not P must also be true. And we can do this by using steps constructed using rules of inference, axioms, lemmas, definitions, proven theorems, etc. Let us have an example. If n is an integer and 3n plus 2 is odd, then n is odd. So if n is an integer, then we can say that its domain is set of integers, and we can express this statement as a universal na quantifier for all n, P of n implies n. For all n, P of n implies Q of n, such that the P of n states that 3n plus 2 is odd, and Q of n states that n is odd. So if we use a direct proof, we start first with the premise that 3n plus 2 is odd, and then prove Q of n is odd. But that will be difficult to prove. We can use its indirect proof instead, or by using the contraposition. We will prove that the not of Q of n, or the negation of Q of n, implies not P of n. So in other words, we start from this Q n is odd. That will be so much easier to prove than we start with 3n plus 2 having odd. So by negating Q of n implies not Q of n implies not P of n, we then get we then prove that if n is even, then 3n plus 2 is also even. So let us try to prove that part. So if its implication is P implies Q, if 3n plus 2 is odd, then n plus odd, its contrapositive will be not Q implies not P. And that will be if n is even, then 3n plus 2 is even. So now, after getting its contrapositive, we can now use a direct proof to this. In other words, we start with the hypothesis not Q. So we assume not Q, then not P must also be true. Okay, so let us see. So we have its contrapositive not Q and not P, and we will start with the not Q, which is n, assuming that this premise not Q is true. So assume that n is even. And by the definition of an even number, n is even if there exists an integer k such that n is equal to 2k. So n will then be equal to 2k for some integer k. And using that, using assuming that not Q is true, we will prove not P is also true. So we have 3n plus 2 is equal to 3 times 2k plus 2. So we simply replaced n with an even number 2k, right? Assuming that n is even, right? So now this will evaluate to 6k plus 2. And factoring out 2 from this equation, we have 2 times 3k plus 1. And we can rewrite it with the form 2j, for j is equal to 3k plus 1. So since 2j has the form of an even number wherein it can be factored out, it has a factor of 2, meaning it is, since it is divisible by 2, it is even, right? So we can say that 3n plus 2 is indeed even. Since we have proven that not Q is true and not P is also true, then we have a direct proof for P implies Q. If 3n plus 2 is odd, then n is odd. So let us have another example. So let us try to prove that for an integer n, if n squared is odd, then n is also odd. So we can rewrite this theorem into its if-then structure. So the hypothesis will be that n squared is odd, and that the conclusion will be n is odd. So rewriting it into its contrapositive, we have the not Q implies not P. So that will evaluate to if n is even, then n squared is even. So after converting it into its contrapositive, we can now use a direct proof. In other words, we start with the not Q. We assume that the not Q is true. So assuming that the not Q is true, we then assume that n is even. So using this assumption, then we prove that the not P is also true. So having n as even, though n will then be equal to 2m. So for some integer m, using the definition of an even number, thus using this not Q, we prove the conclusion not P. So we take the square of the both sides. We have n is equal to 2m, will be then be n squared is equal to 4m squared. And factoring out 2 from 4m squared, this will result to 2 times 2m squared. And we can rewrite it as 2k, where k will be 2m squared. And we have here proven that the not P, or the statement n squared is even, as true. Since we have proven that its contrapositive not Q implies not P is true, we then have a direct proof, or we then have a proof for the implication P implies Q, because they are logically equivalent. So then rewriting the contrapositive, if n is an even integer, then n squared is indeed even. So by contraposition, if n squared is odd, then n is odd. And we arrive to the original statement. Okay,